Hey everybody, Dr. A here, and in this video we're going to be providing an example of static friction referencing the Hibbeler Statics textbook. But before we dive into it, don't forget to hit like and subscribe and be on the lookout for other content like this. All right, let's get started. In this example, we're given a cart with a 7 megagram mass located at its center of gravity G. And then we're given a coefficient of static friction of 0.38, which is in between the surface and where the wheels are resting. And then we're asked to compute the normal force on the wheels, and we're asked to determine if the cart moves. So let's take a look at this figure. We have this cart with some kind of material in it that is being pulled by a 12 kilonewton force that is 1 meter above the base of the cart. And then we have these wheels that it's resting on, and the wheels have a radius of 0.15 meters, okay? So we are considering that 0.15 meters, and you know, maybe the wheels have some kind of casing where they are kind of like also hidden inside some casing inside of the cart there. So we really just care about the 0.15 meter radius for this particular system. So we're also given dimensional lines between the line of actions of the wheels and the center of gravity G. That's where we have a 0.5 meter and a 1 meter dimension here. This is obviously not drawn very much to scale, but this nevertheless is our situation. So the first thing we're going to do is compute the the weight of the cart. So we take 7,000 kilograms, which 7 megagrams is 7,000 kilograms, multiplied by acceleration due to gravity, and we get a number. We're going to get 68,670 newtons. So I just went ahead and put that into kilonewtons as 68.67. Remember that a kilogram meter per second squared is a newton. And so you're going to, when you punch this in your calculator, you get a big number in newtons. And so I just went ahead and divided that big number manually without showing my work by 1,000 to get it to kilonewtons. So let's go ahead and draw our free body diagram now of our system. So our free body diagram, we're going to have our cart. We have the 12 kilonewtons here. 1 meter above the base of the cart, and we have these half wheels here. So here's where you got to be careful. This isn't a box sitting flat on a surface anymore. This is sitting on wheels. So you have to look at all points of contact. We talked about that in the background video. You have to look at all points of contact. So you have 2 points of contact shown in this figure here, right? So it looks like you're going to have a normal force at each one of these points of contact. And it also looks like you're going to have a friction force at these points of contact. Now, where you have to, that was supposed to be N sub A here. There we go. And then F sub A. Now, where you have to be careful is, think critically for a second. This is still a cart, okay? And a cart cannot be supported on 2 wheels. Even though we drew this as a 2-dimensional figure, in reality, this is going to be sitting on 4 wheels. So I'm going to go ahead and put a 2 in front of all of these values here, because in reality, you don't just have 1 wheel at B, you have another wheel. You have 2 wheels at the B location at some distance apart in and out of the page, and the same thing at A. So you really have 2 normal forces, 2 N sub B, 2 N sub A, and then 2 times the friction force, because again, you have 2 wheels at each of those lines, okay? So what do we do next? Well, we're looking at this, and we probably should go ahead and put our weight on here, shouldn't we? I knew we were forgetting something, right? Weight is 68.67 kilonewtons. We're going to put those dimension lines on here as well. And don't forget about your radius of your wheel here. Okay, there we go. Now our free body diagram is done. So we have all of these knowns and unknowns here, okay? So the question is, how many unknowns do we really have here? Well, at first glance, it looks like we have 4 unknowns, right? We have FA, FB, NA, and NB. So we're going to say 4 unknowns, NA, NB, FA, and FB at those points of contact. Now, the applied force, 12 kilonewtons, is horizontal. So we do have a relationship that we can use to our advantage. And what is that? We can say that, put a star here, we're going to say FA plus FB should be somehow related to 12 kilonewtons, right? So we're going to put a little or statement here, okay? So that's another little interesting piece of information we need to return back to, okay? So let's go ahead and apply some equilibrium equations that we can apply and solve for some things that we maybe are able to solve for. Now, did the problem directly ask for FA and FB? Not really, okay? But we need to keep this little asterisk right here in our back pocket for use later, okay? So here's what I'm going to do. I'm going to say, let's do some of the moments about the point at wheel B, counterclockwise positive, equals 0, okay? So if we're taking the sum of the moments about this point right here, this is point B, then FB and NB do not come into play there. And so what can I solve for? Well, guess what? I can solve for NA directly. FA is not coming into play because FA is along the same line of action as point B, but I can solve for NA directly. So guess what I can say? I can say 2NA times the distance in between those wheels, which is 1.5 meters, okay? And then what about that weight? I can say minus 68.67 kilonewtons times its perpendicular distance to point B, which is 1 meter, right? So that is 1 meter, right? Yep. Times 1 meter, okay? And then what about that 12 kilonewtons? Yeah, that's causing a rotation about point B. So that'll be minus 12 kilonewtons, also times 1 meter. It's at a 1 meter height here. All right, and then we're going to say that equals 0. So let's do some rearranging and solve for NA. All right, so we're going to say 68.67, and then add that to 12, and then we're going to divide by 2 times 1. Oh, wait, hang on 1 second. We almost made a boo-boo here. Glad we caught this. I'm not going to re-record this video because we caught it quickly. The moment arm from the 12 kilonewtons, is it 1 meter? No, it's 1.15 meters, right? Don't forget about that wheel radius. So you're going from here all the way down to this surface. Let's change that real quick. 12 times 1.15 meters. Good thing I caught that before we got too far. 68.67. Add that to 12 times 1.15. And then we're going to divide by 2 and then also divide by 1.5. So I get NA is 27.49 kilonewtons, and that's going to be at each wheel at A. Okay, that's 27.49 kilonewtons for each of the wheels at point A. Okay, now I'm going to say some of the forces in the y direction equals 0. And we're going to say 2 in B, right? And then plus 2 in A, so plus 2 times 27.49 kilonewtons. All right, and then minus the weight, so minus 68.67 kilonewtons equals 0. That's everything in the y direction. And guess what? We can solve for NB as the following. I'm punching this in my calculator as we speak. So I get 6.85 kilonewtons. And again, this is each wheel at B. So remember, the cart's really not on 2 wheels, it's on 4 wheels. 2 of them are at line A, and then the other 2 are at line B. That's where I'm getting this coefficient of 2 from, okay? So this is part of the problem. We've part of the solution. We solved for the normal forces on the wheels. Now the question is, does the cart move? All right. So let's think about that. Well, first note, this is not like the box sitting on a flat surface in the previous example where we have to calculate some distance x, right? In this case, we know exactly where these normal forces are. So we'll make a note here. We're going to say no tipping will occur since both normal forces are acting upwards in compression, okay? And again, we don't need to solve for the location of the normal force because we were given that, right? We were given these locations of the normal force. In the other example where we just had a box sitting on a flat surface, we not only needed to find the normal force, but we needed to find where it was located relative to some origin, right? That's where we calculated that x value in the previous example. But again, we know where these wheels are. These are fixed wheels, so we don't need to solve for any value of x. But when we calculated in A and in B, they came out positive, so they are pointing up, which is the direction we assumed them. And remember, if the wheels are pointing at a point, if the force is pointing at a point, then what does that mean? That means that it's in compression, right? Think logically about that. You got a wheel here, you got a force pointing at a point on the wheel. That wheel is in compression, okay? And that force is a compressive force. So since both forces are compressive, then this cart is not trying to uplift or tip over, okay? Now, what about sliding? That's the real question. So we need to follow a similar process that we did in the previous example with just the box on a flat surface. We're going to say FA max is going to be NA times the coefficient of static friction, all right, mu sub s times n. And so our mu sub s, what was that, 0.38? Okay, so we're going to say it's 0.38 times 27.49. So we get a coefficient of static friction of 10.45 kilonewtons. And again, this is at each wheel A, okay? And then we're going to do a similar thing. We're going to get an FB max, and this is going to be, N sub B times mu sub S. And so N sub B was 6.85 and then times 0.38. So we get 2.603 kilonewtons at each wheel B, okay? So again, this is at each individual wheel, all right, at A and then at B. So what do? We need to then compare these friction forces that our applied force must overcome and see what happens. Remember, we ask ourselves, does the applied force exceed the friction developed at these surfaces? And we have 4 contact surfaces. So that's where we pull this out of our back pocket. Remember, we put this in our back pocket earlier. And we're going to say 2 times 10.45 kilonewtons plus 2 times 2.603 kilonewtons equals, what does that equal? 10.45 times 2 plus 2 times 2.603. And we get 26.11 kilonewtons. Now, what this 26.11 kilonewtons represents, this is the total frictional resistance. This is the absolute maximum frictional resistance that is developed between the wheels and the cart. Okay, so we're going to say I'll write it in words, the total frictional resistance at wheel surfaces is 26.11 kilonewtons, okay? And again, that's for contact surfaces, for wheels, okay? And so my question then for you to think about, does the cart move or not? So we're going to say since the applied force of 12 kilonewtons is less than 26.11 kilonewtons, the cart will not move.